So the name of the course is optimization based localization and mapping, and the fundamental optimization problem here is the maximum a posteriori problem. And so today the main thing we are going to cover is the cost function and the factor graph. The outcome here is when you read the paper, you're supposed to look for the information that is condensed in the cost function and the factor graph. So you can quickly skip through the paper and then identify this piece of information. And then that's like 50% of the paper. Then the marginalization and discrete optimization are like just introductory. They are like the state of the art of the research. And we also touch the mapping and loop closure. Loop closure will be related to the assignment. Okay. So the first word in our course is optimization. And I come from control group. And like maybe Patrick can agree with me. If you write a paper and then you frame it as an optimization problem, it's easy to sell. And then when I started doing SLAM, it's also optimization here, optimization there. Machine learning is also optimization. Right? So basically in academic, at least in technical fields, if you frame the problem as optimization, it's easy to start investigating, at least for yourself. And also it's good for the reviewer or the readers to sympathize with you. We're doing on the same thing. It's just that I'm on machine learning, you are in control, for example. The problem statement for our problem is
Daniel wants to ask something, but since I have muted here, we can't hear him.
So it's very simple. Given the measurements you try to estimate your position, I think you cannot like escape a more basic statement. So this is the mathematical notation for our problem. So I actually can skip all of the text and just focus on this equation. So we will use some assumptions to manipulate this problem into a least square problem. We will make assumptions along the way. But why do we have to do this? You think?
Otherwise, it's difficult to solve it.
Yeah, because this is least square with sum of factors, right? So you can solve it in parallel. That's the whole objective.
What is the assumption?
Then in the first one, we're going to introduce the assumption along the way. So first of all, we manipulate this one using the Bayes theorem, And you see, so everybody knows the Bayes theorem. This one is a constant because already given, so it's fixed, so we can throw it away. And then we use the assumption that measurements are independent, so we can break them into separate terms. And then we use the log function to break it into separate parts. So everybody gets to this point without any trouble. I copied this one from Visual Slam. So the assumption is independent measurements. Yeah. So another assumption is that our distribution is Gaussian distributed. So it's simple, like just ignore this kind of like multidimensional problem. Just imagine if you are in a corridor, you have a beacon here. This is your x coordinate. You measure a distance d, right? Then the d is here. And your position estimate is here. So the farther away from this measurement, the less likely your position are. So this is just a simplified example of our distribution.
I'm sorry, I cannot see you. Right.
So I will write on this side. Yeah. And then we just plug the exponential function into this log function, and then you can get almost the form that we are trying to do here. The constant here is because of these components. And the log here, if we assume that we don't know where we are, we just say, okay, everywhere is possible. Then this is also a constant. It's a uniformly distributed, so it's a constant, so we can ignore it. So we recover the least square form that we are trying to obtain.
Why just everywhere where we are.
Correct. We will keep this one in another formulation, but let's just say we try to make it simplest possible. So we keep our assumption uniformly distributed everywhere. So we can get a least square form like this. Okay. So we have a maximum a posterior problem. We use Bayes theorem to manipulate it. We assume independent measurements, and we recover a least square problem to make it solvable. So, okay, so that's how we end up in our cost function. Now for the cost function, we can like start from here. This difference here is a little bit abuse of notation because, for example, you can have like a difference between two rotation matrices that cannot be represented in a vector subtraction like this, right? So this one is called a residual, and this whole least square term is called a factor. They can be interchanged some way. For example, in series, they're going to just call everything residual block. This whole thing is residual block. So it's interchangeable. So now the crucial question is, what information do you look from? Do you look for in the cost function? Just brainstorm.
Like how to minimize it? Where is the zero?
No, you don't worry because, for example, if you already formulate into a function, you just let it solve. So
many factors like factor blocks, and we can have the cost function like this one. Do you mean what's the formula about cost function?
So maybe let me just state.
Sparsity.
Maybe first one, what types of observation we are, this function, what type of observation we are trying to manipulate, to use, right? Camera, eye view, like that.
Yeah.
Yeah.
Oh.
So
But
what
you
types of first information you need to look for is the what type of information.
Before we model the cost function, that's what you mean? Or like I don't really
When you read the paper, right, you see the cost function, you want to know exactly what are the terms.
Okay, what is each part in the cost function?
This means each sensors or each measurement have their own factors, right?
Yes.
Oh.
Most of the time. So the first thing you need to know is, okay, this problem has this IMU, this problem has camera.
Is H the inverse sensor model?
Sorry?
Is H the inverse sensor model?
H is, I don't know what the inverse means, but I think it's straight, forward sensor model. For example, if it's in IMU, it's the integration of the state. Sorry, it's the derivative of state. So the second thing is, what states are coupled with this particular factor? For example, if you have an IMU factor, what states do you think are coupled with that factor?
Corporate? Like
How many states are coupled with that factor?
Position, velocity.
No,
oh.
two.
Oh.
The state at this time and the state at this time.
right.
That is coupled by this
Okay,
integration.
okay.
Camera. If you have a camera feature, here, how many poses do you expect to see?
Only
This
One?
multiple, right?
Because you can see the
Yeah.
same features.
Yeah,
from
multiple
the
camera
different
can see the same feature multiple times. So you need to know exactly which states are coupled with this observation. Another thing is the size of the problem. So it's like if the problem is if the problem has something like 10,000 factors, usually I see that series is low. right? Something like that. It's an implementation issue. And also what kind of robust function they use in their factor. We were saying in an example, robust function means, for example, you do a wrong association and you want to suppress the influence of this outlier in your cost function. So you just trim the magnitude of that factor. So that's the 4 I can think of. Any other idea? Okay, so the factor graph is a visual representation of the cost function, and because it's another medium of communication, so you can actually get something like get a clearer representation of the coupling. We will see an example. Also, some people can put the time progression into their factor graph roughly, and then we also, like I mentioned, some priors into the factor graph.
I have a very silly question. If you go to the previous slide,
Very nice.
the last equation we are on x cap star. So x cap star, if we calculate the minimum argument of this, then we get the best possible x. From here, how do we reach the cost function?
Sorry?
Like from here, how do we reach fx? Like what is f of
Fx is built from a sensor.
okay. So we cannot directly solve for this, you mean? Like why do we why do we need fx? Like why can't we just solve this equation? Or is fx the same
This is the
as
equation.
I think it's same.
it's
Yeah.
the
But
same?
just like
Like this is the function you have to minimize.
Yeah. yeah,
Right.
and
Like in the language of statistics,
yeah.
this is the problem that we're trying to solve in the language of statistics. But because it's not, everything is compound together, you want to break them into a least square problem.
So is P of
Okay.
x given the fx? Yeah, okay, never mind.
So now we find a connection between the statistics problem and the
Understood.
engineering problem. So we just call this whole thing the cost function.
Okay. Yeah. Understood.
So now we want to discuss some terms that are usually kind of stretched in the literature. So what do people mean by tightly coupled? Yeah, I also like see them.
Yes, it means you can't lose one of them if you tight coupled with camera MU and radar. And if one is missed, maybe the whole system will fail. But the opposite of tight up coupled means that autometry can be independent. You can go that front and you can also go to camera autometry. But and not tight coupled, you can get both of the results and do not fuse, and you can use each other. But with tight, it will have same one result, but cannot go. Yeah.
So you're looking from a robustness perspective,
Yeah.
which is a valid perspective. Yeah, I mean,
It's quite engineering work.
I would prefer a mathematical explanation. Means
Yeah.
if you have a tightly coupled system, you just go directly from sensor to the cost function and then estimate.
Uh-huh.
But if you have a loosely coupled system, you use some sensor to fuse together, and then you get a position estimate, pose estimate, and then you fuse it in another cost function.
Mm-hmm.
So that's loosely coupled. It's a spectrum actually. How you design a system is can be very tightly coupled or can be very loosely coupled, but there's also some kind of in between.
So basically, loosely coupled, we can use the sensors we have, but we are not like super worried if we don't have some readings this particular time. But
Yeah.
when we have a tightly coupled, we can lose. We may not be able to estimate.
So you
Yeah,
have
I
a
see.
load and then you have VIO, and then you may have some position
Yeah,
estimate, right?
Yeah.
And then
Yeah.
you have some position estimate, and then you do some logic here to give you the final position estimate.
Yeah.
Lose this one, then this one still can sustain.
It's still-
measurement.
Yeah.
It's loosely. It's very
Yeah.
loosely
Yeah.
coupled.
Mm.
But if you have LiDAR, can you see it again? Please stop.
I don't
Glass
fancy
camera.
I think here not really.
And then from this measurement directly into the estimate. then you get very tightly coupled.
that's what
You can argue for robustness in any way,
Yeah, yeah,
but from a mathematical standpoint, I think at least it's clearer.
yeah.
But that's why Localization is a fake tightly coupled method.
When do you like? When do you do tightly coupled or loosely coupled? Like, why do you choose one over another?
Like in engineering work, because I do some internship on these ones. In engineering, we always use the loose coupled, not tight coupled, because if one failure, the whole system
Yeah.
will fail. We don't want that, and we want the system can hold independent with results. But I saw tightly coupled with academic research always.
Yeah, I agree.
Yeah.
Because it gets better
No,
accuracy.
it has better accuracy,
Mm-hmm.
and you can also argue for robustness in some cases. Like R3 Live, right?
Yeah, R3 live. Yeah.
It's tightly coupled, right?
Yeah, it's tight coupled with.
And they point the camera and light into a wall, and it still doesn't lose track.
Yeah,
So you
because
can't really argue based on the robustness very well, to use that term.
but you may need really great radar MU. It's really expensive MU that R3 Live use.
Yeah.
Yeah, it's not cheap one, but usually engineering work you have to control the money, you know. So you won't get so much expensive MU.
She can teach up to me.
Again, tightly coupled, so you cannot remove factors from any of your sensors.
No. Tightly coupled means sensor stage estimate directly. Loosely coupled means sensor pose estimate somewhere. That pose estimate is fused with whatever again to get you another pose estimate. Okay.
Okay.
Maybe you can watch it. So the sliding window is, I think it's clearer. So sliding window can be like the last, for example, 10 states in your trajectory. It can also mean all of the measurement information in that period. So it's not that ambiguous. Bundle adjustment can also be a little bit ambiguous because sometimes people mean to optimize the whole trajectory from the beginning. But sometimes you also have like a local map that you want to do optimization. It just means that you optimize more states than you normally optimize on the sliding window. So this is not set in stone. You can stretch it however you like. But try don't abuse it so that you're going to bring up an argument with the reviewer. If you have a thin camera, if you put it in that, it's going to trigger another like 3-month review. Don't do that. So we look at the real world example. So this is like our dear OBLAM example, and that's very clear. I mean that's very lovely explaining to you. So basically in this cost function you have IMU and camera, clear. And the IMU is coupling two consecutive states, I and I minus 1, right? Because when you write series code, you have to declare exactly which states you are coupling with this factor. Do it for the solver to update that state. And then this is the camera stage. So you see the index here is not as consecutive like this index, right? It's just anyhow random, right? So we get that information here. This is a robust function because, as I said, sometimes the coupling can be wrong. So you put a function that is going to trim down the cost at a threshold, so it doesn't influence all of the other factors, right?
So how do we select the thresholds? Or is it
You just follow example. I didn't lose sleep by just copying people. Yeah, so this one you can do research on this one, but I didn't lose sleep on copying some basic examples. So if we look into this factor graph, right, I put a LiDAR factor, IMU factor here. It's coupling with the pose, consecutive pose, right? Consecutive velocities. And this is just the bias of the IMU. That is like usually just the bias of the IMU is basically just BK minus 1 plus BK. because the bias you want it to be constant. It's because the model is like a random walk process. So you want to minimize the change of this bias in your problem. You can ignore it here. We can maybe learn more on it when we get to the IMU1.
In this case, for like basically the cost function or in the slam itself, the main idea or the main challenge is to design the core cost function, which is
Yes.
Okay, so that's
Yeah.
like the main task.
Yes, that's 50% of the paper. So I repeat that first. What type of sensors do they use? I'm using camera. What states are coupled with each factor? For IMU, it's the two consecutive states. For camera, it can be any poses that sees this feature. What is the size of the problem? Usually for IMU factor, you have about the same number of factors as the number of states in your sliding window. For camera, it depends on how many features you set into your feature detector in the front end. And they also use the robust function, right? You will see that in they know people put this in the IMU. So IMU is actually a very reliable sensor in that aspect. Couple lots. Huh?
I and J. So what is I and J?
Where is I?
Like inside the equation.
IJ.
Yeah. Like,
IJ means just the two. Yeah. They're just describing this scenario. Maybe J is for the landmarks. J is for the number of features. And I is for the states. Right? So you have to change your perspective. For example, sometimes you have to look at from the feature, and then you see, okay, which states are coupled with it. You keep those indexes in the buffer. Sometimes you have to look from the state, and you see which state is coupled with it. So it's a programming issue. But we got for many information we got from this problem, so we finished like within 50% of it. This is another nice paper. It's more complicated, but it's still interpretable. So what are the type of preparation used? MU, camera, LiDAR, kinematics.
Like all the
Yeah. Kinematics. They read the encoder and they integrate them. They also bring back the prior factor. Just now there's a lock in the beginning of the cost function, so they also bring it back.
So they don't consider it. They don't consider it uniform.
Yeah, they don't consider because, for example, you have estimated up to this point, so you know your position is around this place.
Yeah, like for me, this estimation, like saying that it's uniform, is not really correct, right?
But you can be
It's like
quite
super
conservative, and you say, I don't really know. I mean, they just say at any time I'm also oblivious of where I am, and it works.
Yeah, but you should be a little bit biased, right? Like if
Okay.
you see these things and similar features, then you should be like, I have higher probability to be,
Yes.
let's say, if I look in this corner, okay, I can be anywhere, but with the probability of 90%, like
Yeah.
looking at this
If
corner.
you look in the diagram, you put it into this side, right?
Yeah, as well, but like,
And fine. Then, so from my experience, right, I throw away the margin. This factor, it never hurts me.
or maybe
Because-
if I move and I saw this one as the last measurement, and I move a little bit, then I have a high probability to be somewhere around this area, and lower probability to be on the other corner of
Yes.
the luminol, and then it's like a bit weird to.
But you see, this one right, doesn't couple with any states.
Yeah.
Mm-hmm.
Yes.
Sorry, it doesn't couple with any measurements.
Yeah.
So they actually have there's a mathematical thing to do it.
Mhm.
But let's just recount, right? So prior factor, and your factor, kinematic factor, and your kinematic. This is the MU bias.
Okay.
This is the
Later.
LiDAR geometry. These are all of those things here. They use LiDAR and camera to detect all of those landmarks. And they have like a visual factor. They have the line factor, and they have the blend factor. So, and the coupling is complicated to write, so they use the factor graph to describe. So, right, so that's the learning outcome here.
Leg is like they have another IMU on the leg of the robot.
The robots have the encoders,
Yeah, encoder.
So they integrate those encoders to get you the relative motion.
Like in the wheel encoder.
It's like a
for
wheel
example,
encoder.
this,
If we have like a GPS fix, we should put it in the prior, right?
Yes, yes. No, if you have GPS fix, you mean GPS at that pose or GPS at the beginning?
Yes,
Randomly you have GPS signal, right?
Yeah.
Then it should be in this
Okay,
side.
the measurement.
In
But
this
the
side of the-
beginning should go into the prior.
Yeah.
If I'm okay.
So maybe I'm missing something, but it seems from the mathematical point of view, it sounds like a very relatively simple problem to solve, right? It's not like some super fancy function. So is it like
No,
Yeah,
because
I
they
am not
write
very-
it like this to communicate with you those
Oh.
4 points,
okay?
right?
Okay.
For example, how do you calculate the Jacobian of a line factor? It's when you read the paper in that aspect, that field, right? Like, for example, it's like a DL paper, like 16 page. They're going to have like 5 page to show you in the appendix
Okay.
how they expand these
Mm.
Oh.
into a solvable problem.
Okay. So what
But
we see? Okay.
50% of the problem is just in this description. Like for example, if I'm writing a paper and then this guy is using I'm using camera and I don't bother doing it anymore. So just to have a quick understand. So you see here they visualize the plan, the line, the point in their observation. Clear, right?
And the yellow points which we saw is like the future points.
The yellow dots are the visual points. The green square and the arrows are representing the normal vectors of the planes. The lines are difficult to visualize here.
Yeah, but you have radars, right?
Yeah, they use LiDAR to extract features instead of point-to-point association.
Okay.
So it's like that's why it can be built on GT-SAM. So you need to note that this kind of thing.
Oh, they also do that.
Any question to that? So this is another thing is like beyond traditional single agent sensor fusion, you can also do distributed SLAM. So one drone is flying in one using its own odometry, another is flying using its own odometry.
Can I
Yeah.
go back to the previous slide once? The IMU bias. Can you explain that again?
I think we can wait.
Okay.
Yeah, because it's actually very simple.
Okay.
I see.
When you say the equation, maybe I can show you later.
Okay. Please.
It's-
Sorry.
It's not like worth our time to like explain it here.
Yeah.
Because that's why I put the slides before the course. Right?
Oh,
I put the slide over there already. So this drone is navigating and it's using vision, right? And I'm used to do its own odometry. And then it can measure the distance to a neighbor. And that neighbor is also doing its own visual odometry, and the neighbor can send its position to this drone, and they can fuse them together. So from a perspective of one drone, it's doing visual odometry here, and it's also receiving the ultra wideband range measurements to another drone. And you break it down, visual odometry is just standard. It's the visual factors with the loss function, right? And the MU factor and the prior, right? And then for the range, it's basically the distance measurements and the pose from the neighbor. So it's not just SLAM, it's already beyond SLAM. Right?
Collaborative SLAM.
Yeah, collaborative SLAM. Okay, so now we go to the prior factor. So so it has something to do with the keyword of marginalization. So in the literature, the general meaning is like when you have a sliding window and then you want to put some of your estimates into your database, keyframes, features, landmarks, whatever you want to put into the database, you call it marginalization, marginalizing those information.
Basically taking away some features of all the information
Yeah.
and then saving them, for example, into the
For relocalization, for reassociation later. The narrow meaning is basically you removing them and then you update the prior here. Because like I said, I assume that at every step I do estimation, I don't really know where I am. I just revert my knowledge back to the uniform distribution. But you can.
Does that mean every single step is an independent estimate step? Like as in do you estimate frame 2 from frame 1 independently from measuring from estimating frame 1 to from frame 0? Does that question make sense?
You have a sliding window, for example, 10. That's corresponding to 10 camera frames, and you associate one robot pose to each of those frames. So you're only trying to estimate the last 10 poses.
Okay.
Okay, but the first pose in that 10 frames can have some prior knowledge based on the last stage, right? So this is.
But can I ask a question? Like, if you only estimate the last 10 frames, then whatever I read in your prior won't be corrected anymore, right? Let's stay there forever, or
Yes, it's when it's turned into a prior.
Yeah.
You just try to constrain your states a little bit so it doesn't go all the way, because when you already estimate your trajectory up to this point, right? Of course, it's the next time it's not going to go anywhere. It's supposed to stay around. So you want to use those marginalized information to construct this prior factor here.
What if you have a loop closure like 100 frames later? That would
Then
that propagates back into the previous
yes,
step?
that has something to do with the back end. It doesn't have so far the loop closure at we're not going to discuss loop closure on the sliding window. So far we've been only working on the sliding window, right? So loop closure doesn't happen. I will explain when loop closure happened in the last slide or something today. So marginalization is still a very hot thing. I mean, like these teams, they still work on that and they try to make them useful. So still they still work on it gradually. Personally, I don't like the marginalization factor because, as I said, empirically, I just throw away that factor and I just assume I don't know anything, and it still converges all the time. But maybe you can get out some accuracy, some performance from properly adapting that technique. Oh, okay. This is the fun part. So, cost function and factor graph. What are the four informations we're trying to get? I repeated this the third time, I don't think, right?
What sensors are we using? How big is the problem? And how they are combined together in the cost function?
And the size of the problem,
Size of the
the
Yeah,
robust function.
The robustness.
So let's say,
But do you mean robustness of the function as if they are loosely or tightly coupled? That's what you mean by robustness of the function?
the robust function they use, which means they want to suppress the outlier of this type of sensor and that type of sensor.
As in, like in the case of wrong
Visual.
data associations.
Yeah.
Yes. Okay.
Sometimes you associate the wrong association, so you want to suppress it.
So how they we mean like how they deal with the outliers? That's what.
Yeah.
That's the robustness. Okay. And what?
So the thing I learned is they never actually put a robust function into the IMU factor. So IMU is usually the most robust one.
So maybe I missed it, but did you talk about how we deal with the outliers?
They don't remove the outliers. Let's say you have this edge, right? It's a very wrong association.
Yeah.
So we assume that a majority of the factors are inliers, means they fit association nicely, but there's only one guy. But if that one guy is like making a number something like 1 billion, right? It's going to screw up the whole problem.
Yeah.
But if you put this one into a loss function,
Yeah.
it's going to be suppressed by the other inlier factors. So this should be R square, right? So this factor is not going to screw up our problem.
So it was the curve you drew in the beginning. So you have like a square in the center, and then it levels out. It doesn't matter if it's 5 kilometers away or 1 meter away. You're gonna have the same. It contributes the same to the loss.
Okay, but it's also it counts for the inliers and outliers.
Yeah, in the center, then it's a normal square function, but then it drops off and becomes constant, so that it doesn't. I mean, otherwise, an outlier would completely dominate the cost function.
But then doesn't it matter that if we are very sure about some measurement and then this measurement is correct, it also won't be reconsidered with a high weight to predict the cost, right? Because we're also going to do the same. Or maybe I'm somehow wrong. Maybe I'm misunderstanding it.
Maybe you can.
So my understanding is like every measurement we kind of like push through some function, right? To kind of I say, you know, lower our confidence or like lower the impact of our confidence for pulse estimation. I don't know, maybe.
Let's say we have a sliding window like
yeah.
we have X,
Yeah.
we have T1,
Mhm.
T2,
Yeah.
T3.
Mhm.
We have four factors. This
Mhm.
one is a good association, this one is a good association, this one is a good association, but this one is a bad association,
Yeah.
right? So we have the majority of the associations are the good ones.
Yeah.
And the third one, the fourth one is the bad one. So
Mhm.
if you write each of, because I mentioned like the factor graph tells
Yeah.
you which factors are on which edge, right?
Mhm.
So you're going to have like R1 square plus R2 square plus R3 square plus R4 square, right? So if you choose a loss function like this, and because they are good associations, so they go the numbers, the f function, the numbers are just going to in this region,
Mhm.
right? But this guy,
Mhm.
it's bad association, so the number go all the way here,
Mhm.
right? So it's going to screw up the whole problem because the estimates try so hard to accommodate this bad observation.
Okay, so it's gonna be like a weird drift to go.
So if we just put this row function into each factor,
Okay, so okay, that's what I was saying. So you have to put it on each factor, not only. Okay.
yeah,
Okay, that's.
you,
that was my
you actually don't know which one is our, but you know the majority of them just work in this region.
Yeah, no. That was my question.
So it's a more elegant way
No,
than
no,
to
I-
for every
yes.
factor have to
Yeah,
say
exactly.
inlier, outlier. You don't care.
Exactly.
Or
So
you
that's what I
care,
was,
but you don't have to make that decision. You just make sure that if it is an outlier, it's not going to
Yes.
kill your problem.
That's what I was missing.
Yeah.
Like if we do it for every factor, or we just choose some factors. So that was.
And that means that as measurement, maybe your state estimate changes, then something which was previously an outlier could now, I mean, if you do reassociation.
So now we I spent like a few months of my precious postdoc time to learn how to do SLAM, and I read tutorials, I read some CPP textbook. Then I want to learn how the hell this Chin Tong guy programmed his best paper what transfusion. I mean, I believe he's just a flesh and blood guy. He's just a guy with flesh and blood. He cannot be smarter than me. It's just that he graduated before me. So I go to his code and I use the principle, where is the cost function. I need to find out where his cost function is. So I know in the series, you need to, when you find a cost function, it's solved by that function. Solve. I hit it here. And I do some investigation and I discover, oh, he hides his problem here. So see, very shady, right? He hides it, like that very important line. So you look into my SLAM, and I'm going to put like many comments around that. Just say, look at here, look at here. So let's just isolate this guy. And then what we want to do is you want to know, this is a cost function, right? So there's some numerical representation. So what I want to do is I want to see the cost of it. Right? I want to see what the number is like. I just wanted to know. I mean, I use a J because I'm from control. So I mean, it was F, but just entertain me. Then I say it has 3 factors. So maybe I can calculate the cost for the visual MU and marginalization, the prior factor separately. And if I understand it correctly, I sum them together, I should get the same number for the whole problem. So I call it the sum of the marginalization, the prior factor, and the MU and the visual. By the way, can you see the thing? You can blame Amir for me programming this because I showed him the code and he didn't want to read. So I had to do it one by one. I also want to count how many factors each type has, right? So let's just say I'm going to count them. So if I understand it right, how many MU factors should I have? Should be the same amount as the sliding window. Yeah, around that, right? Because like maybe they put some logic, plus minus 1, the first index is 0 or 1, something like that. But should be around that. So let's just say the cost function is summary. The summary is here. This is calculated for the whole problem. Summary dot initial cost. Right. Let's just say I somehow calculate the cost for the marginalization. Then I add with the cost for the MU, sorry, I0 plus the cost for the visual factor. And then somehow I have the marginalization factor. I say marginalization means the prior, the first in the equation. Yeah, I'm just, this is what I want to print out. I'm going to fill in at the beginning.
Oh, thank you.
You didn't do this, right? You never do this, right? So I call the first, this is supposed to be how many factors of this type of, I have. This one is going to be MU, residual size. Sorry, fat fingers. Then visual factor, right? So this is, I put the 0 there, I mean, I want to see the number, the cost function at the beginning, because if you solve an optimization problem, you expect the number to go down. So you also want to like do another round with the number at the end, right? So instead of initial, it's supposed to be final. Oh yeah, this one has something to do with the assignment too, so pay attention.
Start with like an initial guess, and then you optimize, and then that's going to be the final guess.
Yes. You just try to test out whether you understand the problem right and whether that like flesh and blood guy thinks the same as you. So now, yeah, I mean, it's not going to compile, of course. So what we need to do is we need to look how many factors we are going to find. Supposedly there are 3, right? Is there the paper here? Help me, where is it?
It's way more difficult.
Here. Right. This is the formulation of their problem, right? Three factors. Prior, MU, camera. And you remember this is, there should only be one. This one is the sum of the size of the window system. Maybe if you set it like 9, then you should see 9 or 10 or 8 around that, depending on how they choose the index. And this is the how many camera features they detect. So what we do here is like we try to find those factors. This is we can ignore it because it's just a logic for the localization. So like normally it will not get into this part. This is where this one we set it to like to force. I mean, like estimate TD. So I set to 0 here. So it's not going to run into this part. So it's here, right? So let me do this pushback. Right. So this buffer should count all of the factors related to the camera. And then Control F. Here, MU. So MU residual pushback. Right. So this is the MU. And then marginalization. We can already see how many factors they have. So just need to declare them here, because this is the end of the problem, right? I mean, the function starts here. There are just some declarations here. So vector series internal residual block margin. Yes. Purple JM0 JMK. Just change this to IMU. By the way, I'm not going to claim that I'm getting it compiled on the first try. Who can do it? But yeah, we will fix the error together. Yeah, so I just declare all of the variables that we will look into. Yeah, we already count them. So now I need to calculate them. Calculate the cost. Wait, I think I need to do this. I need to just let me have 30 seconds here. I need to CPP sucks, but what can you do?
Initialize MRS and IMRS and so on.
Yes, I initialize them, but these so I initialize them. That's why it's blue now. So now we need to calculate the cost at the beginning and the cost at the cost before and after the optimization, right? For each factor.
It is the number of steps.
Yeah, it's just like habit. Yeah, you can put it like final or something like that. It's just more typing. What is it? Series problem. Evaluate options. EO number of threads. Don't sleep. Then residual blocks, right? Total marginalization residual. Then problem evaluate. So we are trying to calculate the cost of marginalization factor at the beginning. EO JM0. No.
What is the null? Initial.
I'm happy to copy people's code. It's just some costs, some harbor loss, and whatever harbor loss. So for the purpose of the demonstration, we don't really need to worry about them. We just need to worry about the numbers, right? So this is what visualization.
That's one question.
Mhm.
But what's I think I lost myself. What's JMJI?
J is the cost,
Cost.
the specific number of that F.
You can control your cost. J.
Oh, I thought it was Jacobian.
Oh yeah, my bad. But like, what can you do?
Okay.
Uh-huh.
Sorry?
In MPC, if you go MPC, which is global conversation, like,
Uh-huh.
record with video.
Okay.
You know what MBG is?
What is it?
M is marginalization, means the prior factor. It's just that in series they call it the marginalization. So
Okay, so they have some map before and then.
no, they don't have SMAP before, but what I said is they remove some states. So your states, sorry, they remove some measurements and states. So your new state must be around the old state. So they try to constrain your estimate around that prior information.
Oh, okay, that's why it's not uniform.
Uh-huh.
Oh, okay.
So
Mm.
I call it the marginalization because implementation, they call it the marginalization, but you can call it the prior factor. Can it combine?
Yeah.
Let's see, yeah.
Those.
1 minute? Yeah.
Perfect. Yeah. We can have a break.
Yeah.
You only, so you could also build only this package, right? Like the selected package. I'm asking because you only change one.
I know, I mean,
Fine.
like, I asked, I mean, whether you would be able to, I would, if I show the code, I already coded. Would
No,
you?
no, like you do can build now, right?
Ah, yeah.
That
It's done,
can-
it's building the things now.
Yeah.
Keep on. Keep on by.
Well done.
Oh, him. Yeah. So, I need to take that. I forgot to take that. So what do you expect? You will need to wait for him? Or
Yeah.
Yes.
You don't want to like break the. Shouldn't we keep the questions to once? I mean, I don't know. I mean, I have a flow, and then there's a question, I get interrupted. I
We
don't
can
know.
try.
Quick! I compiled already.
What?
Compile in one go.
Yeah.
There's no error. So
Congratulations.
proud of myself.
Congrats.
So we have. I was trying to. So probably the second one, we have like double the number of slides. So maybe I have to cheat into the tutorial time.
Yeah.
So today the key point here is you look into a cost function, you need to take away 4 pieces of information. That's all. And then we're trying to verify our understanding here. Did your group study Vin's code?
Huh? Not really because we study R3 Live because Venus is quite old.
Yeah.
Yeah.
Actually, live is like filter based,
Yeah.
and it's built on top of fast IO.
Mm-hmm. And there are fast level 2 also? Or?
Fast IO 2 is the same with Repo.
Yeah.
So you hit pull, it's the same. It's good. Make her teach.
Oh no, I'm
You
not.
you have 80 something hours in the TA.
But it's more like a teacher assistant, right? So I did that.
I mean, I teach once, next year you can teach.
Oh,
Do
I
more,
can be the assistant, but not teacher. Sure.
I think we shouldn't. So okay.
We're still waiting for Lee.
Should accommodate a 5 minutes break.
Sure.
Let's see.
But would you appreciate more if I just copy them out, or you would appreciate me if I code it like this?
No, I think it's good that they call it.
Yeah, correct.
Yeah. No, I mean like you should accommodate 5 minute break for like quick bathroom or water refill. So.
So if this is serious, so it's solved. What about GGSAM?
I use GGSAM, but I didn't.
I think GGSAM is
It's means use GGSAM or GTO. Oh, use SLAM. Oh, LeoSAM is use GGSAM.
I think it's magic function is the update. Yeah. Right. So they build a graph and they update. So that's what I mean. When you do this kind of thing, you need to learn a few tricks. So basically, if it's by starting from a principle, there's a flesh and blood, a human being somewhere coding these kind of things from some principle. So he can't do some magic that you can't imagine. So you probably have to start from the same place that he has to do it. For we have OBLAM here. Yep. OBLAM uses GTO.
Yeah.
So I think the magic keyword is optimize. Yep. So that's how you do it. You start from the principle and you just test it out from that. And the reason, and so like maybe you can make another solver and then quick. So you know what we've been doing, right? I compiled it already, right?
Yes.
So now waiting for you to see the magic. So this is the car park next to our lab in NTU. And so you see starting cost and the final cost is smaller than the starting cost. 600 compared to 637.
What does it tell us?
It tells us that the optimization
It's great.
It optimized.
Success.
yes
No, but what does the number tell us?
doesn't tell you much actually because you choose the weights yourself. So I can scale everything down and I can get to 60 something. It doesn't matter, but you know, okay, it goes down. Our sum is the same as so our calculation is the same as the calculation for the whole problem. So we understand the range, right? And we count the number of factors. So yes, 1 prior factors, 10 IMU factors because the slide window is about that. And then 1,000 feature associated with cameras. So we understand it, right?
Is this also value also set somewhere like keep only 1,000 features? Let's say it's like
Okay, yeah, so good because like you see it works, then you want to tweak it, right?
yeah.
I think we can like go to this and increase the number of features to 300. See, so if that visual factor should increase. I don't know. I mean, maybe not. Let's see.
Yeah, it's increased. Like 500.
Yeah. So cause and effect, you increase the number of features, you're supposed to have more association. The cost increase. Cost increases slightly compared to just now.
It decreases. It keeps on decreasing. It was like 1,000, now it's like 500. Or maybe I'm missing something.
Yeah, maybe
Just
more.
change the cost, right?
I change the number of features. So the immediate effect is that you see more visual factors here.
Yeah, but the cost is actually lower, right?
Now it's bigger.
Now it's bigger, yeah. Now it's bigger, yeah, but it was like
in
300,
this
right?
sliding window.
Yeah, it
Yeah.
depends on the image you showed, the features in the image. So
Okay, so it
you
depends on
cannot compare the different frames about the cost.
So what we learn is the type of observation. We figure out, okay, this one has 3 type of observations, and prior and
But so,
feature.
is there any intuition how, because like, okay, so for me I see the number, but I don't know if it's a good number or bad number, like I just see, okay, this we do optimize it, right? But like what does this this number tell me? Like nothing really.
It's the number is correlated to the noise. I mean, in theory, it's correlated to the noise of the sensors that you declare.
Mhm.
Right? For example, for IMU, if you put the noise of the accelerometer to be 1 to the power of -5 or something like that, then if it's very wrong, you can get billion.
Okay, but then still it won't tell me much if the end will be 500,000.
Yeah,
It's like-
it
is
won't
it
tell you
okay?
much because you can try to track down all of those numbers and scale them down,
Yeah.
and
Like,
whether you will see the number of the cost goes down.
so why is not like I don't know why we don't scale it to 0 and 1 to the value between 0 and 1 to like be able to.
Why would you want it to be between 0 and 1?
Because then we would get like a better overview of like what is the current cost function. Like you know if it's like really huge or if it's like we are lowering the cost functions actually to
That is only
minimum,
relative,
to the minimum, right? Because
but that is only relative between the sensors. It only matters between the sensor, right?
okay.
For example, if you have this sensor, and then you want to increase the weightage of this sensor in your optimization program, then you can increase the weightage.
Yeah.
But if there's some like engineering fine tuning here by the author, I just keep his numbers.
Okay.
So he said he made it set over there. I mean,
Like I don't argue that it's wrong or good. I'm just like trying to understand better like why this number is just like a random number and is there a way to just maybe make it more intuitive, at least intuitive for me. So
do I have to? So like for example, this is the experiment I'm running up there. So you see the cost here is like only 20 something.
yeah, and again, does not tell me
Yeah,
anything.
it doesn't tell you anything. The only thing you need to worry about is that it goes down.
Okay.
And then if you do like that experiment and you say, okay, my number is usually only 20, 30, but then this experiment it goes to 100, then I screwed up somewhere. Right?
It's like a loss
Loss
function
right?
in
Loss
deep
function also
learning.
does not tell you much. Yeah.
It doesn't tell you
goes
much.
down. Yeah.
The sheer number doesn't tell you much.
Yeah.
It's the trend. It's
You
the
see-
relative trend.
So you just want to see the trend. Okay. So it's
Just now I have only 4,000 visual factors, right? So now I have like 4,000. So
Yeah.
just now I had only 1,000 visual factors. Now I have 4,000 LiDAR factors.
How do you, it's related to this question. So how do you know when like this optimization is good enough?
It's good enough when the change of your cost is very small.
So when it's stabilized, yeah.
Ah,
Yeah.
Or
okay,
just,
okay, okay.
just
Because it's already
the loss.
settled at the minimum.
Okay.
So you see here the change is actually very small.
Uh,
It means that my prediction is already quite close.
Yeah.
Right? So it doesn't actually have much room to improve.
What if there's a local minima? Like, is there like some mutation and exploration?
Can you also argue the same with machine learning?
Yeah.
So I also argue the same.
No, but there are.
If you predict very well, you're just around the global minimum, right? If you predict, because you can do prediction, like I said the other day, maybe up to 1 second. So if you do prediction very well, then you can like be sure that you estimate somewhere near the true estimate. Okay. Back to the slides. Where am I? That would you inspire? Are you inspired to go jump into another piece of code or something like that? Or do you think this is so tedious?
I think it was very useful.
yeah.
So so this is just like, I think the last 2 or 3 years people have been doing discrete time optimization. Means if I get a LiDAR measurement, if I get a LiDAR point cloud at this time, I'm going to create a state estimate here, right? And I'm going to try to design a cost function that couples only these states for the LiDAR, for example. Because the LiDAR, you have like for the LiDAR, right? you have a 128 channel, you have 1 to 24 vertical beams, right? And this is like 0.1 second period. So you can actually get the points at millisecond timestamp different. This point and this point, it can be like millisecond different. So you can't like create one state estimate at every time. That's going to be like 10,000 states for you to estimate. It's not solvable. So you try to just constrain the problem with like a few states according to some meaningful time steps. This one is pegged to the point cloud frequency. Right? So I create a new state every 0.1 second. And I can use the IMU to compensate for the time difference here to bring every point into one time step and then design cost function around that. It's been the traditional way. So, but then it becomes so at one point people realize, yeah, you don't need to do it. You can actually treat the times separately, but you don't. But you, instead of like estimating with 1,000 states, you are now solving the problem with maybe 10 states, but 1,000 states is not possible. Maybe you can solve it at 20, 30 states. So there's something between. And what you do is you, this one is a little bit, so you try to create a interpolated pose in your trajectory. So this is the point measure at the time, at any time on this sliding window, right? And then you try to find a pose at that time, and that pose is interpolated by maybe the two closest points, right? So this is the sliding window. I have like this many states that I can manage in my optimization problem. I have a measurement that goes here. Then I can try to find the pose at this time, TS, right? And this one is linearly interpolated between these two states. So I can create a factor that couples instead of 1, now 2. Then another more fancy way is to model your trajectory by a continuous curve using the B-spline formulation. And there's a library for you to do it. And then the principle is basically on your slider window, you can, and then if you're looking into one period, right, you can use, instead of two closest points, you can couple this state by interpolate by another rule that has the weightage with consecutive poses. We do this because our measurements come at arbitrary time.
And they're not synchronized. Is that the problem, or is it?
Yeah, it's not synchronized. For example, if you have two cameras, right? If you have two cameras, maybe the camera is 10 hertz, maybe 30 hertz. So camera 1 goes like this, right? Camera 2 like this. So it can be arbitrary time.
You might have a LiDAR that fits at 240,000 points a second. It's a lot of.
And also it's not 10.0 hertz, right? Maybe it's 9.8 plus minus.
Yeah, then it can be some jitter back and forth. So you have to find a way to make your trajectory continuous, manipulable in a continuous time manner. And the way we do it is they use the interpolation. So you can use a linear interpolation, means the time of the measurement can be coupled with the two closest time, or you can couple it with the most several points. Several points mean you use the B-spline method, right?
So the discrete time optimization, they didn't do that. They didn't do.
The discrete one is the traditional one where they try to like circumvent this problem by using IMU prediction to bring all the point cloud to the one time. So instead of the pose, the point being captured at. So instead of building the factor with the point captured at that exact time, you build a factor with the point that have been transformed to the time of the state estimate.
But if,
This is just good to know.
but, if it's like, for example, LiDAR, it's like milliseconds, then the interpolation and the way they use IMU to do that, they should be, sort of like have similar performance, right? I don't understand why this is like
so let's just say because agree with me that you only can solve your problem if your problem has that many, maybe like 100 states, right? So let's just say this is time tk1 time tk plus 1 in your problem in the time window. This is the pose. This is the time, and then the measurement comes here, and it comes here. And what do you do? I mean, what do you do?
pick a few of them.
Pick a few points?
Yeah.
Like you pick 3 points, then how? They do at these different times. Huh?
But it's time based. You cannot average like if you at 0 in time 0 and 19 degrees in time 2, time 1, and you cannot set average like.
But at very short of time, I can really trust them more, right? I can trust there is like little drift.
Yeah.
So you mean you use IMU to do what? What do you use? What do you use the IMU for? So let's stick with his suggestion. So what do you do with the IMU? So the point, like you measure a point, and then that point is in the body frame at the time of the sampling, right? TS. Yeah. What do you do with the IMU? That's actually assignment 4.
Estimate like a pose.
Yeah, you estimate the IMU pose to P, B, K, right? And this is the traditional way. So instead of dealing with this continuous time LiDAR point, we just deal with this IMU compensated point. That's what people have done in discrete time because you only have this many states to handle. But now there's a paradigm when you just instead of this IMU1, I just do the interpolation here between TK TK minus 1 S this one TK no, this is plus 1 TK plus 1 TK, right? Linear interpolation. But then this one may be not enough, then you do BS spline interpolation. Baseline interpolation principle is the same. It's just that you couple with some more states after this.
Instead of taking one measurement to interpolate, it's making continuous time.
Yes. So you still have with a finite number of parameters to optimize, but you can deal with arbitrary number of measurements. So it's good to know. So maybe should I test it? It's better. It's better. I mean, at least the experiment I was running just now, the slick code, it's better. So just now I'm biased to series. So there are 3 that we know, right? That I know of. Series solver. Then the G2O and then the GTSAM. And to the best of my knowledge, I see that people use series for the LiDAR and Visual Slam. For G2O and GTSAM, mostly only Visual Slam. I actually have, you have any experience?
I have experiments on GTSAM in planning, but not in that.
So why does LiDAR, why the series? Why is series compatible with LiDAR?
Visual features, and it doesn't matter really if it's
Yeah. Around that, you're close. Because, for example, if you have a feature here and then you have a pose here, then this edge is set, right? You do some association, and then all of the parameter set, you put it into the graph, leave it there. There's no update. But if you have a point cloud map, right, and there's this voxel with maybe 4 points, and then you add another point cloud into your map, then maybe 6 points, then the statistics of this voxel changes. So you have you cannot like modify your graph every time, right? So you have to go back to the fundamental one, which is the cost function, right? So you have to calculate this voxel again and change the numbers. So that's why I say it's easier to use series to handle that kind of thing. So yeah, at the end of the series, it's more versatile because it's at a lower level. It's more on the cost function. But when you start to use GT-SUM or GTO, you have to accept that it's from a factor graph framework.
Yeah, you just need to add the Jacobians and
Yeah,
like that, and
once a factor is fixed, when a factor is created, it's there, it's not changed.
Yeah.
But for series, you can change it at every time. But don't like stick with my maybe I'm biased to series, but series.
Yeah.
It's just the name that Google chose. GTO is global graph optimization or something. GT-SUM is geodetic smoothing and mapping.
we normally use GPU and GT-SUM actually. And in companies, we choose the GPU, and in academic, we choose the GT-SUM. But I knew the system, but I didn't use that before.
Why?
Because in lab, other people are using the GPU and GT-SUM. You can ask questions really.
Okay. It's
That's
legacy.
Yeah,
It's a legacy thing.
Yeah, it's based on the life.
So we go to the problem with the map. So what is the importance of map in localization? So the other day, Patrick said that it's not very important. What did you say? I forgot.
I said we don't care about, I mean, if we, in this course, we're going to treat the map as something that allows us to reduce drift and increase accuracy.
Yeah. Yeah, I agree. But I think the way I phrase it is map is crucial because you won't you won't be able to do any of that with a map module somewhere in your code. But it's not prominent. Yes. The marginalized information, it could be marginalized the other day. It could be marginalized in the last second.
But I think that's where marginalization comes in. I mean, if your end goal is to do mapping, then I would say marginalization is super important. You want to lock your estimate into where it was previously. If we do control, localization and control, we really care about having a smooth estimate of where we are right now. And we'd rather have a map fly around.
Yeah. Yes. So I would say that map is crucial, but it is not prominent. It's not prominent because, like, from my experience, 80% of the time that I develop a SLAM is like on the front end. The cost function, how I calculate the Jacobian, how I figure out how to associate the data, right? It's like very time consuming on that aspect. But then once you fix that front end, then you just spend maybe like a day, then maybe or so to finish the map and the loop closure. So the back end is actually quite easy. Not that hard to get it to work. Of course, if you don't have to worry about the real time and then you just go home and then just fill the map together, then you can do another research topic on it. So that's the importance. So like, it's crucial, but it's not prominent in localization. But if you do research on map fusion, it's not fit to this statement. It's okay. So what are the other uses of map? So the latest trend I see is like 10 years ago, it's very hard to get ground truth in an outdoor environment at a large scale. But now if you have money and time, you actually can survey and then scan your campus or your environments very accurately. to millimeter accuracy. And one of the most prominent uses of this is that you can register your LiDAR with the map to get you millimeter. For example, centimeter is also quite good accuracy. Which this is the data set that I'm doing. So this is our campus KTH, and this one is NTU. This one is by Oxford in their Sheldon Theatre, and this one is in Oxford in their campus. So I think it's very expensive. But oh, wait, so just to tell the story. So this is the beauty data set that they did, right? And I submitted the result, and somehow my trajectory error is at number 4, but my survey score is like at the number 10. Because they score separate the sub 1 cm accuracy from the 10 cm accuracy very well. So it just happened that it's like, I mean, if it's number 4, I actually could win a few $1,000s. But at least we got KTH onto the leaderboard, right? So local map and global map. If you look into the Wins Mono and OBLAM, you can always see, okay, there's this local map here, and there's this local map here. This local map here. So the question here is, why you have to employ a local map? Why?
Next move or like your next predicted state?
I don't think so.
Local map is the sliding window, right?
Yes, around I mean, other information around the sliding window. Because when we talk about sliding window, usually we mean the balls and states.
Yeah. Local maps like maybe 3 seconds prior, right?
Yeah.
Yeah. So I think it's like my
But if you look into this experiment, this scenario, right? If I'm doing localization here, and I have a scan that goes all the way here, right? I don't have any map here to associate, so I can drift relative to the starting position. But let's say I have the whole map to do association. My scan can be associated up to this point, so I can reduce the drift relative to the starting position.
But that's the global map.
So the global map can be useful, but why do people have to use the local map?
To run your system in real time. If the global map is too big, it's maybe too time cost.
Yeah, it's close. Because, for example, if you have a visual feature, right, and then you want to associate it with the visual feature checked in another frames, if you treat everything as a global map, treat all of the keyframes as the same, you have to search like thousands of previous keyframes, right?
Yeah.
And it's very like inefficient. So probably you just need to worry about association in the last few keyframes. Yeah. So the reason why is efficiency and the complexity. But then we can do local map, at least for LiDAR, I know we can do local map. Like FastLiO, they use the IKD3 and they use the global map. So the reason is because for this particular type of point cloud map, you can incrementally update it. Right? Every time you want to associate with the map, point cloud map, you have to build a KD3. So if your map grows, that time increases. So, but if you can find a way to incrementally update that tree over there, then the time is the same for all of the updates. So you can do association with a global map. Understand?
Because the incremental means it cannot change.
So you put the new data into your tree, they can rebalance the tree and then quickly help you query the voxel, for example.
If this map size increases, the time taken to rebuild or like readjust the tree keeps on growing and bounding.
Yes.
You want to keep localize it,
Yeah.
keep it constant.
Yeah. So if you find a way to incrementally up the map, you just bump a point cloud into the map. And then the voxels that are updated will be updated. The voxels that won't be updated. So the time is bounded. So that solves the problem. Our code will be published. So, okay, this one is related to the assignment. So loop closure is cover like to the depth in Visual Slam. You remember anything? I also don't know much like detail, but I get the general idea. For example, if you have a keyframe image keyframe, they're going to do some histogram of the visual descriptor, and then if you go back and then the descriptor is similar, then you say, okay, you're back to the same place, right? And then you can do some endpoints, perspective endpoints to find the relative pose. And I build Visual Slam, and I really don't care about the detail. I just copy the label block, put into my code. It works. I'm happy. Move on. It's true. So for the loop closure, there are 3 main steps. The first one is you have to know you actually are back to a place that you visited, right? Okay, you have to know, because if you just go on, even if you visited, but there's no signal to trigger the whole thing, you still go on. So for image, we can use the traditional method called the back of world by OBLAM group. For the point cloud in the assignment I designed, it's supposed to be based on the k nearest neighbors. In the literature, people have been using intensity image from the LiDAR point cloud for that kind of. So it's the principle is kind of similar to the visual part, but it's based on the intensity image. And in the DAPA challenge, we can also see some papers that use symbols in other way. They just carry some ultrawideband beacons, and they casually drop them on the way. So when they go back to the same place and the distance measurements is within 1 meter, it's a very strong signal to confirm that you visited the same place. So the second thing is we need to calculate the relative pose between now and then, right? So if you use camera, then you have to find features, match them together, use the marginalized position to calculate the pose. Right? For our assignment, I use the just simple ICP to align them. It works like 1 kilometer trajectory, and then this one works. Maybe 10 kilometer, then it's not work. Yeah. So the third one is we optimize the pose graph. Means if you throw away this term, the loop term, the cost function is going to be the same before and after, because you're going to use the current poses to build the cost function and then optimize it. But there's no loop, so the number is going to be the same. But then if you put the loop in, it's going to pull this pole back to this pole, so you can see the number changing. So the red parts are supposed to be done by you. This part I already handle for you. So your job is to come up with a strategy to recognize the previously visited place and then design the post-graph optimization problem. You might end up not improving anything, even though you build a cost function and optimize. So if you do everything nicely, we can see something. So that's the nearest neighbor. The blue points are the nearest neighbors. Then you go back to a place that you visited, and then you start doing ICP. I start doing ICP. You don't handle the ICP. And then when ICP gives a pass, then we build a loop closure and fuse and optimize it and then bring up the loop. I mean, close the loop.
For that, or you use for that path, what are the system requirements to do it? Or I don't know if you'll discuss, but like you said that there are some system or like this memory requirements.
I mean, so if you only optimize with one loop, one last loop, then you may end up failing the optimization problem. So you see here, it's not one loop, right? There's a sum here. It's multiple loops. It's multiple loops. So you have to keep detecting loops and add it into some buffer and somewhere, and then keep adding these factors into your cost function.
And then, like, what are the memory requirements
Oh.
on your laptop to run this stuff? That's what I went for.
I think 30 gigabytes will do. Yeah.
30.
Like my laptop, that's early.
This laptop has 32.
Oh, you have 32.
Yeah.
You have like a nice. I kept like 128. I mean, like I'm doing during the Christmas. It's not gonna be like an SSH.
Yeah. Let's see. How many is the oh it should 20. Yes.
Yeah, I mean, Ajinga says fine, so it should be fine. I trust Ajinga.
Yeah.
20 gig. I think so 20 gig should be fine. 16 gig should be fine. Huh? Of course, I pay like $5,000 for it.
Don't worry, if you have enough memory on swap space, maybe it will not crash, because I crashed my computer when I trained something, and it full with swap space also. So don't worry about if the memory is full, it will move to swap space.
I know.
And
You should have enough
ridiculous
RAM, right?
different.
You should have enough RAM, right?
I do on my PC, but like I won't be here during the Christmas break, but I will be working from home, so
See, the
then
RAM
that's
didn't
the time
increase.
where I will have time to do this.
So yeah, I think around 16 gig works.
Like
Yeah,
remote,
Hopefully.
doing stuff remotely on
yeah,
PC.
it's like 20.
like
Yeah.
Teams or any desk
Yeah.
stuff.
Okay, so any question back to the beginning, from the beginning? See, exactly 3. That's why I was kind of rushed.
I had one question. If you go back to the slide, I think just the slide before. Yeah, I think it was here that you mentioned something about.
Maybe for the question, maybe we could swap so that you turn off your microphone and we turn on the room's microphone. Is that-
Okay.
Oh, right. I have to join first.
Can you stop recording if you need to?
Hello.
Recording in progress.
Hey,
No, I can hear something.
Yeah, no, you should be able to hear me very well, at least.
you can
Tim, you need to turn off
Close
your
your-
mic.
You go.
Maybe
decrease your voice, like.
Start
This guy
recording
joined,
this
so that's what he said.
Yeah.
Okay, question. What is the
Oh
question?
yeah, no, I was just thinking, because when you were talking about assignment 3, you were saying that we could like build this loop closure thing and then build graph optimization thing, and then you see like after you finish off and nothing, you don't get any better results. So like, if you're there, what do you do?
the reason, so I tried this assignment,
Uh-huh.
and I was trying to like put my mind into your mode, and
Uh-huh.
I just like try to finish this assignment, right? And I just like optimize with the last loop that I detect.
Uh-huh.
You may detect multiple loops on the way, but
mhm.
I just optimize with the last loop.
Oh.
Then I get the result out and I do the calculation, and I realize there's no change.
Uh-huh.
So just to play it fair, I mean, like I recommend you to save your loops in a buffer somewhere. And when you do optimization, just pull out all of those relative poses to optimize together. Don't ignore the old loops.
Ah, okay, I know what you mean.
But,
Just, so it's like I added maybe 3, 4 more lines.
Ah, okay.
Because just a vector, put the number in. No?
yeah, but could we just, once we detect a loop and then we optimize like the whole graph, and then when I detect another loop, I optimize this loop.
Yes, I did that. But then when I finished optimizing the last loop, right?
Yeah.
The error at the first and the first like just like went back to normal. You know what I mean? So it's like this is the just now the trajectory come back here, right? And there was a growth. This OBLAM. So when you go back here, right? And then you do loop closure, you're going to go close the loop, right? So you're going to see the trip disappears. But if you just throw away that loop and then you keep estimating,
But you haven't thrown it
optimizing,
away, you have optimized the form.
you have to keep the loop that you detect here. You have to keep the loop that you detect at that place.
Yeah, but if you have optimized already a post graph, that information should already have.
Not if you optimize it again and don't have that constraint anymore. Then
Yeah.
Oh, okay, I see.
So somehow it's going to close the loop nicely at the very
Yeah, yeah.
late point. But the drip at that point just like came up, appear
Right,
again.
right, right.
I have another question. If there is a loop and then it starts, it keeps following the previous path, there will be like so many loops detected here.
Yes,
like
yes,
it's
yeah.
continuously loop closing. Then wouldn't it be super slow?
It's very slow. So that's why you see in this implementation I actually put a 5-second threshold for loop closure for you.
So
Oh,
do it
you-
every
you-
5
you
seconds.
construct it,
I
right?
think I put 5-second threshold there for you already.
Oh,
Did
we
I? I
have,
don't know.
What do you mean by 5-second threshold?
So if you already close the loop,
You won't be able to close it again.
I don't know,
for the next 5 seconds.
I don't know, I mean, maybe I didn't, but if you encounter that very slow thing because of multiple loop closure, improvise yourself.
Oh,
okay.
It's realistic problem.
yeah, no, you're right. You're right.
But ideally
I
you
don't
want
want to
to
like
keep,
open the code and then maybe I reveal everything.
ideally you want to keep detecting though. Like you would have run that in another thread. But you want to have all these loop closures, or you think they're not important? Like, is it important that we?
I think you don't need too many loop closure. Yeah. You can space them out. Doesn't hurt a lot. Okay. Any other question? So assignment number 2, I just like cover the first part, which is the cost function. If you look into the assignment number 2, it's supposed to be going to the piece of code right up from what is it? Simple. I've done it already for you. But the second part is some mathematical manipulation. So the math is there, but the math is already there, but it's in the CPP language. It's not in a nicely LaTeX font. So you can actually like do what I did, dive into the code, make hypothesis, confirm it. Just know that the guy is just a flesh and blood, and then just graduate 1 year before you. There's nothing like that.
Question: when I look at that equation or that cost function,
Uh-huh.
the equation looks very daunting. So all the terms there, like the camera factor, LIDAR factor,
Mhm.
are they always the same? Like, so you have read 20 previous papers. If there's rho times something, it's basically the same factor for
Yes.
all the papers.
Yes.
Unless you have like a cylindrical camera model, like a different camera model, or like a event camera, then it's different. But for a camera,
But when they write it, they are going to use something like R,
yeah,
V. So you know there's something with camera there.
right.
And then they, in the next section, they're going to go into like visual factor, and they're going to explain to you what the visual factor is constructed. Like what it's like to construct a factor.
Hmm.
Maybe they use of discrete feature, or they use direct method,
Right.
like some kind of intensity there. I think it's the same, but they also have a factor there. Mhm. Yeah. I guess I have to eat into the tutorial for the next one, because the next one is about the so today we only have 4 points to remember, and then the this lecture we also only have four points to remember. This one I call it the 4 noble truths. You're going to not exactly doing this, but like at least you know there's a methodological way to approach it. Just like you asked me, what is the most complicated thing about the thing is deploying these 4 steps into each sensor. Okay.